I don't have any questions, but I will say it's very messy, but it's doable.
Yeah, it's messy, but at the end of the day, it just
Yeah.
all just like comes together, if you like,
Hmm.
right? And yeah, by the third time or the fourth time you derive it, you basically have everything memorized. So I've done it maybe, I don't know, 10 times in my life.
I'll have to do it 2 more times, I guess.
Yeah, so, maybe 10 times, maybe more.
Maybe 20.
Yeah, I forget. I mean, every time I teach it, I have to I love teaching this. This is just a very uh, pretty nifty thing. It's a very weird thing, right? I mean, uh, because, let's make some comments. So one of the applications of the finite path integral is the double slit experiment. So two slits, and so the particle. Suppose you've got electrons coming out. So there are all kinds of paths the electrons can take, but really the dominant, the path that are interesting here is the path that the electron takes this way, and say here. So that's say path number one, and then the electrons takes the path here and here. So the electron is effectively free, so there is no potential. So you just have to compute the action for a particle with a given kinetic energy, say a given velocity, for these two paths. And the calculation is exactly the calculation you did in optics. But now you are interpreting those things as phases, as actions. So you calculate this and you find exactly the interference pattern that you think. So this is interesting because Feynman is saying that and you might say, what happens to this path, say. So that path is also there. But what's happening is that, that path is going to be canceled by other paths which are kind of symmetric around this path, okay? So they will cancel those paths. So the contribution is from those two paths. So now suppose that, you have a screen and you have another screen here, and this is your, sorry, let me just switch to my usual color. You have a source here, right? And so what happens is that classically we say that if this was a particle, let me redraw this. The screen is up to here. So classically, this is the geometric shadow, like this part. This part of the screen, this screen is in the geometric shadow of this screen, right? Of this screen, correct? But what do you think? Do we see any light here, according to classical optics and electromagnetism?
No, some fringes except.
Right on the edges, we do see some light. It's called diffraction, right? So classically, it can be explained classically. But what if this is like your source is so weak that you are emitting one particle at a time. So in the previous case, suppose your electron gun is extremely weak, so that on average there's one electron at a time. So you wait long enough, you will see that the interference pattern forming here. So even though the apparatus has only one electron at a time, it knows of both slits. And that's perfectly well explained using the Feynman path integral, right? Because the electron goes through both slits, because it's a quantum particle. Now here, what happens when you have a source which is so weak that there's only one particle in the whole system at a time? Over time, you will also see a diffraction pattern, build up here. So how do you explain that? The way to explain is that, Feynman had an intuitive explanation, and you can make it actually more, what's the word? You can make it quantitative, and Feynman does that in his book with the Hibbs. And the idea is that, suppose that this, barrier was not there. Suppose that this barrier was not there. And, then the electron would actually be, and the electrons were all going in this direction. Then the electron would just go here, right? So in that case, okay, let me explain it in a slightly different way. Suppose that my barrier is like this. Okay, and this is easier for me. And then basically what is happening is that, everything over here is in the geometric shadow, and everything here is in the geometric shadow. So there is this little gap here where, if light was just classical particle, that's the only place you will see light. So, but we end up seeing light here. I'm exaggerating this distance, by the way. And why is that? Because, according to the path integral, there would be trajectories like that. And that's a non-classical trajectory, right? Because it's not a straight line. Because the classical trajectory can only bring you here. So this would be a non-classical trajectory. But there would be other trajectories nearby which would also, bring you to this point. But in the absence of the barrier, so if the barrier was not there, all these trajectories will cancel out because it's not the classical path. And therefore, as you vary the trajectory, delta of S will not be 0. It'll be quite large. And therefore, the contribution from all the paths to this point, would cancel out. But when you put a barrier, what you do is that some of these paths are now blocked because your barrier is blocking, so yeah, sorry, I should have drawn these paths like this. You have paths, you have paths like this. Because there's a barrier now, some of these paths are blocked. So, the 0 that you got, you had to add an infinite number or a large number of phases. Say these phases were like randomly distributed, and they added up to 0. But now, what is happening is that a lot of your phases have been taken out by the barrier. So as a result, the resulting phase is no longer 0. It's a non-zero phase. And therefore, there is a non-trivial amplitude and therefore a probability that the electron or the quantum particle will actually reach into the region of geometric shadow. And this is a very elegant way of describing the diffraction using the path integral. Okay. Did you guys get the idea? It's a fun it's a fun explanation.
Yes, sir. Yeah.
Okay. So let me make some comments. And I was going to derive the propagator for the free particle, but I don't think I'll have time today. So I'm just going to end with some comments. And this was a repeat lecture, right? But I think when it comes to stuff like this, it's good to repeat. These are non-trivial stuff, non-intuitive, non-trivial, and intuitive if you think of these things for a long time, because this was definitely a very intuitive explanation, right? Of course, you can explain all of this by using Schrodinger equation, because then you have a wave, and therefore waves can kind of spread out and blah blah, right? But Niels Bohr. Okay, let me put that in the comment. When Schrodinger had, and when quantum mechanics was first formulated, Niels Bohr, formulated the principle of complementarity, right? Do you know about this?
I don't think I know about this.
Anyone else?
Okay.
Yes or no?
No.
Yeah, you don't know about it because I'm the one who taught you quantum mechanics, and I never told you about this, so it's my fault. So the principle of complementarity is saying that there are some experiments experiments which reveal the particle nature of light or of quantum particle, and there are other experiments which reveal the wave nature of light, of quantum particles. Okay. For example, the double slit experiment is something where the wave nature of quantum particle is manifested. On the other hand, if you look at quantum scattering, that's where the particle nature of quantum particle is manifested. So what Feynman said is that with the path integral, there is no need for this principle. Because the quantum particle is so weird that it encompasses all the different situations, right? And I believe there's a history. So Feynman made a comment in a footnote in his popular book called QED, The Strange Theory of Light and Matter. And he makes a very uncharitable comment about the correspondence principle in that book. And I think I know why he was so uncharitable towards Niels Bohr. Because when Feynman first presented his path integral in a conference in, I think it was about Shelter Island or something, no one understood what he was talking about. It was only, I think, Freeman Dyson who understood it. And Niels Bohr interrupted Feynman, or at some point in the discussion, he interrupted Feynman because Feynman was talking about trajectory of particle, and Niels Bohr interrupted Feynman and tried to explain to him the Heisenberg uncertainty principle, saying how a quantum particle cannot have a trajectory, because then you would have both its position and momentum well defined. So Feynman was amused because he knew that Niels Bohr had completely misunderstood what he was trying to talk about, and he was trying to teach him, quantum mechanics 101, which of course Feynman knew extremely well. So I think that Feynman's uncharitable remark about the correspondence principle in his book called QED stems from that from that interaction. So anyway, so I wanted to use this opportunity to also introduce the complementarity principle, because whether Feynman likes it or not, it is a nice principle that has served physicists well. Okay, so that's comment number one. Comment number two is that the configuration space path integral consists of paths which are smooth as well as zigzaggy. Okay, so I know that zigzaggy is not a very technical term. What I mean is that, so the particle starts here and ends up here. So this is, and what happens is that the particle, so this is, say, the classical path, but the particle takes all paths. The particle can also take paths like that. So the thing about the zigzaggy path is that they are continuous but not differentiable, right? Because over here it's not differentiable. So the zigzaggy paths are, if you look at x of t, so this is a path, right? So this will not have a well-defined derivative at these points, and that's fine. So what's happening to the momentum of the particle at this point is changing suddenly, right? And so if I look at how this integral looks like in momentum space, so that means that if you're looking at the path integral in, in phase space, then the momentum part, so this is, say, p, and this is t. So, the particle continues its momentum for some value, and then suddenly it changes and becomes like this. And then suddenly it becomes like this. And suddenly, oh, sorry, I missed something. And suddenly it becomes like this, right? Something like this. And, then there, for another path, the particle starts at a momentum like that, and then suddenly it changes, becomes like this, and then this, and this, and say this, and this, okay? And similarly, for another momentum, initial momentum, it does something like this, right? So,
So I had a question about the diagram. Isn't the phase space supposed to be like P versus X? Like we just have like
the
P,
next part
T
will be the
here.
same as here. That's what I'm saying. Yeah. So, yeah, this is not the.
Oh, okay. Yeah.
Yeah, that's good. So, so basically, for the phase space, the momentum, the momentum part of the trajectory is discontinuous. Okay. And actually, in quantum mechanics, the idea of phase space is not well defined anyway. And the last comment I want to make is that inside the path integral, all quantities are classical. It's just that the measure itself is something it's a monstrous thing. And that's really what makes it a quantum object. Okay, so I'm going to stop here. And Nahi asked me a question on Slack about how to prove the fact that the propagator is the solution to the wave equation with source. I would like, Nahi, for you to try, thinking about it, say, in this terms, say x prime x ut minus t prime x prime, and then inserting, say, some identity, some energy eigenstate and stuff. Also use the fact that we want the propagator to be 0 when t is less than t prime. So that essentially what I'm saying is that disturbances should not propagate backward in time. Okay? So I'm not going to give you the answer today because the question about the properties of the propagator, there's so much richness in the propagator that I want to do a complete whole class on that after we are done with the path integral. Okay, so because of that, I'm not going to answer your question now because there's some beautiful contour integrals, some theory of idea of Wick rotation, and I want to cover all of that after I'm done with path integrals. Okay.